Craig Knoblock is the Director of Information Integration at USC, their Information Sciences Institute, where he leads a team of 20 researchers, staffers, and students in doing various interesting things. He's here today to talk about his work on detecting and extracting structured data from raster maps. So please put your hands together and welcome him.
Great. Thank you, Michael. Okay, so I'm going to talk about work we've been doing now for a number of years. The title of my talk is A General Approach to Discovering, Registering, and Extracting Features from Raster Maps. And as you can tell from the title, there's a lot of different stuff to cover. So really what I want to do is give you sort of an overview of the different pieces of technology we've developed over the years and try and give you a sense for the kinds of problems that we've solved and are currently working on. I need to acknowledge my collaborators. So this is really joint work between USC and Geosymbol Technologies, which is a spin-off company from USC that's been commercializing some pieces of the technology. And there's a number of other researchers and people that have completed their PhDs that have worked on this. So Jason Chen, Yaoi Chang, Aman Gol, Matthew Michelson, and Cyrus Shahabi have all contributed to various pieces of this technology. Okay, so as you probably all know, raster maps are a very rich source of geospatial data. They're often easily accessible. They often contain many different types of information on the maps themselves, lots of different layers, lots of different interesting kinds of maps, and they often contain information that you cannot find anywhere else. And so, you know, the challenges are how to actually find and exploit that information. So a couple examples on the slide here. So on the left we have a travel map of Tehran, which is quite detailed. You know, it has all the names of the streets. You can't really see it in this picture. It has, you know, locations of gas stations, all this kind of interesting stuff that a traveler might want to know. And on the right, we have a USGS topographic map of St. Louis, Missouri. And I like this map just because it has a lot of detail and also has a lot of historical information. The USGS has these topo maps going back into the 1850s. And they contain a lot of interesting sort of historical information about where the roads were, where the buildings were over different periods of time. Okay, but some of the challenges in actually extracting data from maps are that while they have a lot of information, they often have this problem that there's a lot of overlapping features on the maps, making it often hard to get the information out of the map. There's often very limited access to the metadata, so we may know the general area the map is of, but we may not know things like the scale of the map, the geocoordinates, other sort of key pieces of information that you'd like if you're going to combine this data with other sources of data. And often they're only available in raster format. So most maps, at least current maps, are typically created from vector data and then turned into raster data. But often what you have available is just the raster data itself. And older maps were created by hand and then, you know, converted into raster at some point. So there was never a vector format for those maps. So the challenges are, how do we actually find these maps that cover a given area and a given topic? How do we register them, meaning how do we actually figure out exactly what the coverage of the map is? And then how do we actually extract the different layers and then recognize the features in those layers in the raster map? And so I'm going to talk about all of those things today. Okay, so here's the outline of my talk. I'll give you a brief description of some of the work we've been doing on sort of map discovery, how we can go out and find maps for given regions. Then I'll describe two different techniques we're using for doing the automatic extraction of the different features. These are the different layers in a map, like the road layer or the text layer. So I'll talk about automatic techniques, and then I'll talk about some more recent work we've done on detecting the layers or extracting the layers from very noisy maps. Then I'll talk about the automatic registration of these different kinds of maps. You know, how do we actually figure out, you know, the relationship of the map to satellite imagery? And then some recent work we've been doing on feature recognition, which is actually pulling out the content from these different layers. And I'll conclude with some related work and discussion. Okay, so map discovery. So what we want to do is basically collect candidate maps from the web. And we've essentially been doing this with two types of maps. First, we started with looking for standalone maps using things like image search engines, you know, Google Images, where you could go and you could type in the name of a city and maps, and you get a whole bunch of things that might be maps. And then we discovered that, well, some of those are interesting maps. Most of those are relatively low-resolution maps. And so I started looking around and discovered that many of the really interesting maps that you could find on the web or embedded in PDF documents, partly because PDF has some nice facilities for actually storing maps, but also maps just tend to be embedded in larger documents and stuff. And so then we did some work on actually extracting the images directly from PDF documents. And then the challenge is, if you have these images, so if you use an image search engine or you find a PDF document and you pull out all the images, then the challenge is how do you actually figure out which things are actually maps? So we developed some techniques where we identified a set of features that can be used to sort of characterize maps, and then we use a technique called content-based image retrieval, or CBIR, to try to figure out which things were maps and which things were not maps in terms of the images. So here's the basic approach. So along the top here, you see a set of images. Some of these things are maps, some of these things are not maps. And so the basic approach is to take each of these images, extract the set of features from the images, find similar images. And what we did here was we built two repositories. One was a map repository, which essentially is a large collection of things that we were known to be maps. And then we had a non-image repository here shown on the right side of the screen, which are the things that we know that are not maps. These are things like pictures and figures and things that are not maps. And the idea is to essentially find similar images and then to essentially classify this final image based on what it's most similar to. So if we found that it's mostly similar to other maps, then we'd say, okay, this is likely to be a map. And if it's mostly similar to other non-maps, then we say, okay, this is probably not a map. So you can see at the bottom here, we've taken the images from the top and classified them, and what we hope is output from the system is then the classified things that are actually maps. And we played around with a number of different features, but the feature we found that worked the best were to use a set of things called water filling features. And the idea is this is really a way of looking at a certain kind of structure in the image. So it turns out that maps, I mean, if you look from a distance, most of us can look at an image, and from a distance we can recognize whether it's a map or not. And that's typically because it has very strong sort of line features. So it has very strong edges. So what we do is we essentially start with a map like the one shown on the left here, which is a map of different, I think, political districts. And we create a canny edge map from this, which is really just the map of all the edges. So we really this makes it color invariant. Since maps have a whole variety of colors, we didn't want to build a map recognition tool based on the colors. So we're really just looking at the line features. And then, if you see the little area that's circled here, we pull out some set of edges here, and then we compute the water filling features on these edges. So this is just so you can see what's actually going on. It blows up the image and shows this one part of the image here. And the water filling features consist of three things. They're what's called the fort count, the filling time, and the water amount. And essentially what these are doing is capturing the properties of the lines, right? And this is really capturing how long the lines are, how much the lines branch, and the total number of pixels that are basically contained in all the lines here. And so for each of the different lines that are contained in this edge map, we compute these things, and to make the properties sort of size invariant with respect to the size of the image, we then create this normalized histogram of these different features. So what we end up with is a feature vector that consists of these three features for this sort of normalized histogram of the different sizes of these features. And so we can essentially feed this into this technique I mentioned, this content-based image retrieval, where the idea is we take our map repository and our non-map repository shown at the top. We run it through the CBIR method, which essentially says, all right, we're going to take the image, we're going to do the feature extraction on the image, and then find those images that are in one of these two repositories that are most similar, okay? And so it's going to generate and this on the slide here, it shows the 5 most similar ones. And then it essentially is a voting system, right? So if you say, well, the top 3 are basically maps, and then the next 2 are non-maps, then this is more likely to be a map than a non-map. And so it essentially does, a k-nearest neighbor classification, where it's essentially looking at the voting scheme here. And this just shows the number of votes, but we actually weight it based on the similarity. So we do have a feature strength in terms of how similar each of these is in terms of those 24 features, and we decide which one are maps. So that gives us pretty good results. We ran this on a test of 8,000 images with 4,000 images, 2,000 maps, 2,000 non-maps, and a separate test set. So we trained it on the repository, and then the test set it was similar size. And the kind of results we're getting here are precision, which is pretty good, 77%, recall 71%, which gives us an overall F measure of 74%. So it's not perfect, but it allows us to quickly classify those things that are more likely maps, so then we can go on to the later stages of processing. So we'll see as we go on in my talk that really the purpose of this is to quickly identify which things are likely to be maps, and then in the later stages, if something's not a map, then it's going to fail the later stages in the processing and would get filtered out. Question back here.
So are you more likely to throw things which are maps out, or throw garbage into your maps?
Well, okay, so the recall, we're more likely to throw things away because we have 71% recall, so it's lower recall than precision. So you would like to, you could adjust those though. You could, if you wanted to tweak the numbers. But what we found is there's a lot of redundancy out there. So, there's lots of maps. So if you're looking for maps of a given region, so maybe you missed some, but there's so many maps out there that you may actually find other ones that cover the same area and the same themes. Okay, so now I'll go on to the next topic. So I've talked about how we might go out and find maps automatically, but maybe you already have some maps as well. So let me talk about some of the methods we've developed for doing automatic extraction of the different layers or features from the map. So if we look at an input map on the left, so the basic problem here is that you have a map and you want to essentially pull out, initially you want to pull out the road layers and the text layers. Okay, so those are what we focused on, although the same techniques would apply to other kinds of layers. And so what we want to do first is remove the background information. So if the input map shown on the left here, and what we have on the right here is a grayscale histogram of the actual pixels in the map. And as you can see, some of the pixels are much more types are much more common than others. And what we want to do is figure out which ones are the background pixels. So you can see we draw this line here from the 0, 0 point on the axis up to the highest point on the histogram on the right. And then we drop a perpendicular down. And if you drop perpendicular down, you find those points that are essentially those lines, those perpendiculars that are essentially the longest, okay? And those are the things that are going to actually segment the histogram into separate pieces. And the one on the right here is most likely to be the background color, because the background color sort of tends to be the most common pixel color on a map. And so we can essentially divide this up into different groups, look for the dominant number of pixels, and then essentially remove that from the actual map that you're seeing. So you can see on the map itself, we can go from one that has this sort of shading in the background to one where we can pull it out, and what we're left with is essentially the road and the text layers. And this works for a wide variety of computer-generated maps. Once we do this, now we're left with something that looks like this, where we have both the text and the road information on the map. So the next step is to actually come up with some way of actually separating the information into both the road layer and the text layer separately. So to do that, we essentially look for these small connected objects, which tend to be the characters. And this is from the obvious property, which is, road lines tend to be long and connected, and characters are going to be relatively short. And so we're going to look for all the characters and essentially group these into these connected objects, which are essentially the strings or the text strings on the map. They may also be the symbols on the map. Once we pull those out, we can remove these connected objects, and we're left with the road layer. Although you notice there's a little problem with our road layer, which is that in many cases the characters overlap on top of the road layer. And so by removing the text, we end up breaking up the road layer here. So you see there's some places where it's now disconnected, and we're going to have to fix that. But this gives us the initial sort of data to work with. So we have the road layer now on the left. We have the text layer on the right, which are all those things we removed. And the next step is to actually recover the missing characters on the road layer. So to do that, the first thing we want to do is actually identify some of the properties of the roads itself. So many of the interesting maps actually tend to be double-line road maps. And so we developed this technique called parallel pattern tracing, where the task is to actually figure out if it is a double-line road map and what's the pixel width on that double-line road. Right? So if we know that, that actually helps in further processing. And if it's a single-line roadmap, we want to know that as well, because we do different processing for that. And so what we do here is we essentially look for, we essentially assume a certain pixel width and then test to see if the map is what the properties of the map are. So for example, if we assume that the road is a 3-pixel width wide road, then we can look and see if this this pixel, so here it shows this yellow pixel on the map, and we can look 3 pixels away, and we can look to see, well, how many of those pixels are actually filled in, right? And if it turns out that if this is in fact a 3-pixel width wide road, then we're going to find that when we look at this pixel width compared to other ones, that we're going to get a large number of pixels exactly that distance away. That's going to dominate this distribution of pixels. So in this case, you can see the road opposite, the roadside opposite the yellow one is 3 pixels away, and you're also going to find some other pixels 3 characters away to each side. Now, roads can be at angles and so on, and you won't always see that, but overall, this is going to be a property you're going to find overall on the map. And so what's going to happen then is we're going to essentially iterate through. We're going to say, well, okay, let's consider whether or not this is a 1-pixel width wide road map, 2 pixels, 3 pixels, up to something like 10 pixels. And we'll look at a graph of all the pixels, and you'll see a spike at the place where it's actually a double-line road of that particular road width. So once we apply this technique, what it's going to give us then is the road width. And if in fact it is a double-line road map. And if it's not, then there's not going to be any peak in the graphs. So that then is going to give for this map shown on the left here, once we know the road width, then that allows us to extract at other layers. So we can actually remove, for example, these topographic lines on this road, because we know all the ones that are not 3-pixel width wide roads are not actually roads. But we also, you'll see later, we'll use the fact that this is a road width of a particular size in further processing. Okay. So here, the next step is to actually reconnect the broken road lines. So what we really want to do is end up with a topography of the roads that's accurate. So those roads that are connected. Since roads tend to be connected, you don't end up with a bunch of separate road segments, right? So we're trying to basically go back and reconnect the ones that were essentially broken when we removed the text layers. So to do this, we go through a series of morphological operations that basically allow us to reconstruct this road layer. So the first step is called dilation. And the key here is, now that we know the road width, we know how many steps of dilation we can and should do on this particular map. Since it's 3 pixels wide, we know that you're not likely to put another road 3 pixels or less next to those roads, because then it would be very confusing to actually look at that map. So we can do the dilation. We know how many steps in dilation to do. Then we go through a step called erosion, which then shrinks the road back, but hopefully leaves those roads that were connected, that should be connected. And then finally we go through a final step called thinning, where the road width then goes back to being a single line road. So the final set of roads we have are all 1 pixel width and width. So, and this is very useful for the further processing. Okay, so we've gotten back to single line roads. So now we've essentially extracted the road layers and the text layers. And this is great. This works on a lot of computer generated maps. So you can run this on Google Maps, Yahoo Maps, any of these online maps. Any map that was typically generated in by a computer and has certain properties. So for example, it has detailed roads, the map was drawn to scale. We can automatically process these maps. But the challenge is that there are many maps that aren't as clean as these, right? They're not generated by a computer. So for example, here are 2 different maps that you might want to process. The one on the left is in fact a scan map. So this is the one of the maps from USGS. And these maps were originally drawn by hand and then scanned in, and scanned a long time ago using a relatively poor quality scanner. And then the map on the right was one that was we purchased online. It was shipped to us, and then we scanned it in. And you can see, if you look carefully, like the background colors here have different shades where the map was actually folded. Okay, so that the coloring is not consistent across this map. But even if you look at the map on the left, the number of pixel colors that make up the roads, even though it looks black, there's, I think, 8 or 10 different pixel colors that actually make up those roads. So these maps are very hard to process in a completely automated way. So, here's one of the difficulties, the fact that they contain many, many colors, just because, for 2 reasons. One is because the scanning technology tends to produce lots of colors to sort of capture all the variations in terms of the different pixels. So this map here on the left had 285,000 and some odd colors in it. And if you look at the grayscale histogram here, you can see there's a whole distribution, wide distribution of colors to represent, by the eye, it just looks like a few colors, right? It really looks like, fewer than a half a dozen colors on that map. So what we want to do is come up with a way to deal with these kind of maps. So first we go through a process to do some color segmentation where we reduce the number of different colors we have on the map. So the first step is to use this mean shift algorithm where we can essentially look at the color distance between the pixels in the RGB space. And this allows us to essentially take pixels that are very close in this color space and merge them into a single color. So that gives us a good reduction, a factor of 2 reduction from 285,000 to 155,000. It's still too many colors. But this helps us in the second step. In the second step, we do a k-means algorithm where we're going to limit the number of colors to some number k, and we determine that number experimentally. And we go from 155,000 to 10 colors. So if we give the algorithm the value for k and run it, and it generates a map, and basically you can tell whether or not that was a good value for k if you can still distinguish the roads from the other features. All right. So we end up with a grayscale histogram you can see on the right that has 10 lines in the histogram. Okay, so what's required from the user in this case is now just to identify the roads themselves, to provide examples of the roads. So our goal here is to be able to process a wide variety of maps with really minimal user effort. Since there's a lot of tools out there where users can do a lot of work to extract information, our goal is to make this as simple as possible. And so our user labeling is essentially requires the user just to provide us an example of each of the different road colors. So if you look at this map here, you can see on this particular version which has the reduced colors, there are really just 2 colors for the roads. There's the white roads and the yellow roads here. And so what the user would do would simply identify 2 examples where they simply point to the center point of those 2 roads. I mean, anywhere on the map, some center of the line. So here there's one label on the white roads, 1 label in the yellow roads. And then what we do with that is we basically take these examples and we decompose them into the number of colors. So let's assume that I gave it, for the purpose of this slide, a k value of 6, since I couldn't fit more than 6 squares on this slide. What we do is we now take the label on the left and decompose it into each of the 6 colors. So each of these squares has only one of the 6 colors from the image. And what we want to do now is determine which one of these, or which ones of these 6 colors correspond to road pixels, right? Because our task here is to figure out the actual road pixels on this map. And we do this by essentially applying a technique for detecting what are called the hue lines. And this is essentially a technique for drawing a line or set of lines between that runs through the center point of the pixels on a given image. So if you look at the 6 images on the top correspond to the 6 pixel colors that we pulled out. And then the 6 images on the right, one of them corresponds to each one of the ones on the left, on the top rather. And this shows you the hue lines. And the hue lines, okay, are in 2 colors on the bottom. The ones in the red are the ones that are within some distance of the very center of the image. And this is important because remember, we asked the user to label the center of the road lines. So if there's a lot of hue lines, a lot of red lines rather, then that means that most of the pixels are running through the center of the image, which means that they're likely to be the actual road pixels. The blue ones are the ones that are farther from the center. So this is really just shown here so you illustrate this point, the red and the blue colors. And you can see the colors that correspond to boxes 0, 1, 2 clearly have more blue lines than red lines. 3, it's kind of a toss-up. And 4 and 5 clearly have more red lines than blue lines. And so those are the ones we're going to say, okay, these are the ones we're confident actually correspond to road pixel colors. Okay, so we can essentially determine the road colors on those and essentially combine these. So we say, okay, we're going to generate this road template by taking these colors that correspond to these 2 types of templates, and that's going to generate the colors that we're going to actually identify that are likely to be roads. So we can essentially take this color template, apply it to the map, and then generate a map that looks like something on the right here. So you can see we went from this map on the left, which originally contained lots of different colors in it, to the one on the right, which contains mostly the road pixels. And there's a few areas here that are still filled in, and we have some ways to remove those. But I'm not going to talk about that today. But we essentially are applying some additional operations on that to get rid of these large solid areas and to reconnect some of these lines. Okay, so that gives us a technique then to essentially take maps that may be very poor quality in terms of the scan quality and also due to compression have lots of different pixel colors and to extract out an accurate road layer. So I'm sorry, this is the final map. So once we go through the morphological operations, we end up with a fairly good quality road map here from this original raster map. Okay, that brings us to the next step, which is to actually do this automatic registration of the maps. So what we've done so far is I've described, techniques for essentially pulling out the road layers and text layers automatically. The next step is to figure out exactly how this map relates to other geospatial layers, right? Because we really would like to understand the precise coordinates of the map, and then to be able to apply transformations on the map to essentially be able to overlay the map on top of satellite imagery or other geospatial layers so that you could visually see the information on the map overlaid on other data sets. Okay, so the basic approach is shown here in this picture. And the key idea here is to essentially exploit the layout of the intersections found on a map and compare it to the intersections on an image or in a vector data set. And the intuition here is simply that, if you have a large enough area, the layout of the road intersections is going to be unique. Okay, and you're looking at the actual, trying to find the similar layout on the image or on a vector data set so that then you can essentially do the mapping between the map that you have and this other data set. So what we have shown in this image here on the bottom, we have a map, a raster map with some unknown set of coordinates, right? We don't know the coordinates of this. And we're going to detect the intersections on this, and I'll talk a little bit more about how we do that in a minute. On the top, we have a road network, okay, and this is like a vector road network, and this is relatively straightforward. We can just detect all the intersections by just searching in this vector road map to generate all this, and these corresponds to these red dots here for the detected intersections. Then we need to do a point pattern matching, and I'll describe briefly how we do that. And then the final result would be the actual alignment between this map piece that you're seeing here and this vector layer here. And we can come up with the exact mapping, not just to the corner points, but we can actually map each individual road intersection to the corresponding road intersection on the other data set. And that's actually quite useful because then we can do the actual process called rubber sheeting to align that map with the image. Okay, so let me first talk about the problem of detecting the road intersections. So I've already talked about pulling out the road layer. So the next step then is to actually detect the actual intersections themselves. And to do this, we apply a technique called corner detection, where we essentially look for every place that there's some transition or change in the direction of the pixels. So you can see this happens both at the intersections, but also happens in the middle of a road, perhaps where because of pixelation, the road jumps over one pixel there and looks like it's sort of, but there's a simple technique, so we can pull out all these corners. And then what we want to do is figure out which of these corners are likely to correspond to actual intersections. And for the purposes of what we're doing here, we're going to assume that intersections actually require at least 3 roads that come together. So if you have fewer than 3 roads, we're going to discard it. But if we have more than 3, then we're going to say, okay, that's a road intersection. So that's how we generate the set of road intersections. But we're not quite done. Because what we really want to do is generate a road intersection template, right? And this is not just the location of the intersections, but what the intersection actually looks like. And the problem is that in that processing for pulling out that road network, one of the things that happens is we may actually end up distorting the actual road lines. So you can see that here in the top image, where this is the actual road line that got extracted from the map. And you can see what happens at the intersection. It gets distorted because of the morphological operations that we applied, which do this filling in pixels and then removing pixels to try and reconnect the roads. And if we just extract the template directly from this, then the template we would produce would look like this one in the center here. So you can see this template does show 3 roads comes together, but doesn't show the actual angle the roads actually come together in. And that's a bit of a problem. What we really want is the template on the bottom here, which shows an accurate road intersection, which shows how many roads come together, the location or center point of the intersection. Notice this early template here in the middle is not centered, and the exact angle that these roads are coming together. Okay. So how do we fix this problem? So we essentially start with the approximate location of the intersections, which was, in the original algorithm I described for pulling out the intersection location. Right? We have these thin lines, right, that we've pulled out of this, which are distorted. And then we also have the intersection positions, which we also pulled out when we detected the location of the intersections. And what we're going to do is we're going to combine these two. We're going to first say, all right, based on we know the approximate width of the road lines, and so we can create this blob that basically covers the entire intersection. So we can take those intersection points and create a blob, and the size of the blob is determined by the distance between the road lines, right? If it was a 3-pixel width wide road, we know how big to create these blobs. And we're going to overlay these blobs on top of the actual intersection points. And then what we do with that is essentially extrapolate from the lines themselves back into the intersection. So if we say, okay, here's the general direction of the road lines, that over the distance that we're looking here, we can actually extrapolate these road lines back to the center point, and we can essentially correct for this distortion. So we end up, instead of the distorted intersections here on the top, we can end up with intersections that actually very nicely capture the location and the geometry of the actual intersection points. And this is actually really important for several different things that we're going to use in the future, do in the next steps here. The first one is the point pattern matching. So the next step in this, now we've found the intersection points, is to actually figure out the relationship between these intersections and this other vector data set. And in this process, we use not just the location of the intersections, but the actual template of the intersections to do the matching. So as I said before, we use essentially the distribution of these intersections to determine the relationship between the map and the image. And so what we're doing is essentially finding a mapping between these points. So on the left here, you see we've extracted some set of intersection points. There's 80 points here on this map. And on the right, we have the intersection points that have been identified on top of this image. And we're looking for the mapping between these two. Okay? So we're essentially trying to find this transformation between these two. And the advantage of actually having accurate templates, like I just described, is in that search process, we can actually search for those templates that actually match, right? We can search for ones that actually have the same number of roads that come together, same angles, and relative locations are the same. So we do this search to find this transformation and come up with this mapping between the map points and the points on the imagery. Given this transformation, then we can apply this technique called conflation or rubber sheeting, where we essentially look at the mapping between all of the intersections on the map and all of the intersections on the image and come up with the actual transformations that we're going to apply. And this is important because if we want to just take the corner points of the map and superimpose it on top of the image, you may not get a very good alignment simply because we don't know certain things about how the map was created in terms of the actual projection that was used and other details of the actual construction of the map. But by doing this, we can essentially apply a set of local transformations that give you very good alignment between the map and the image, so that the labels that are shown on the map will actually be shown in the correct place on top of the image. So we do the rubber sheeting, and you end up with a result like this, where you can see the labels correspond directly to where the roads are. The details from the map are superimposed on top of the image. Here's an example of imagery from Baghdad. So the upper left-hand corner is an image from Google Maps. On the right, we have a map that corresponds to the same area, and then we've automatically processed this map. And so and then on the bottom left-hand corner, we've superimposed this map and made it semi-transparent. So now you can see the labels from the map are superimposed directly on top of the image in the correct place. And on the right, we've actually pulled out the text layer here and superimposed it. And so now the labels are simply superimposed directly on top of the information that's in the original image. So essentially, by going through the steps I've described so far, we pull out the different layers and then automatically register them with respect to the imagery. Now we can do one of our first goals, which is simply to allow you to essentially use the map to essentially label the image. All right. We'd like to do more than that, though. So, that gives us, visually a useful piece of information. what we really like to do is go back and construct the original data sets here. So we want to construct something that corresponds to the actual data sets that you could use to create a map. In particular, I talked about extracting the road layers and the text layers. And so what I want to describe now is how we can actually build up the actual data sets that correspond to the vector layer and the text layer. Okay, so the first one of these is the road layer. So really what we would like to end up with is not just a raster layer that shows the roads, but to actually build the road vectors. And I mentioned earlier that the fact that we have very accurate intersection information really helps us in terms of doing this vectorization process. Because the most accurate way to do the vectorization is instead of just just taking the map and trying to vectorize it, and there's commercial tools to do this, what we do instead is we actually say, all right, we're going to start with those road intersection templates because they correspond to the actual center points of the intersections, and then they contain the directions of the roads and the number of roads. And we're going to do the vectorization from starting from those points. And so you can see here on this, it sort of gives you a sense, is that you start in the middle, and you're basically going to essentially do the extraction of the vectors based on those road templates. And we get a very nice result doing that, a much better result than you would get if you just tried to take the whole extracted road network and say, well, just turn it into a vector layer. So this is an example result that essentially shows the road vectors superimposed on top of the original map. So the road vectors that were built here are shown in red, and then it's just superimposed on top of the map, so you can see how the vectors we created correspond to the original roads. And you can see the result here is actually quite good. You'll see some weird things that happen on the edge, and that's simply you get some weird, strange results as you get close to the edge of the map. So that gets fixed when you stitch these the tiles together. You end up with nice vectors along the edges as well. If we look at results, I don't really have time to go into the details here, but just to give you a sense, so we tested this on 16 maps from 11 different sources, and we compared it to a commercial tool called R2V, which is probably one of the better commercial products for doing this, which is an automated raster to vector conversion software. And in terms of completeness, correctness, and quality, which are really measures of the correctly extracted road data relative to the false positives and true positives here. You can see that across the board, our system, which we call Strabo, did better than R2V. And the numbers that really matter here have to do with the overall sort of completeness, correctness, and quality, but also the redundancy. So it turned out that what was happening here is that R2V would get high completeness by having a tremendous amount of redundancy in the data. And redundancy is a measure of how many times they were extracting more than one pixel for the same road pixel. So you can see the numbers there are very large. So they'd end up with lots of little extraneous lines. Now, we could have gotten better results with R2V if we'd spent the time to really tune it with a bunch of manually specified sort of pre-processing and post-processing functions. But as you recall, one of our goals here is really to be able to do map extraction here with very minimal sort of user input. So we didn't want to do a bunch of training on this. Okay, so that's the results in terms of extracting. You can see the results are actually quite good in terms of the quality of the actual data that we're able to extract, the road data that we're able to extract. The second piece is to actually do the text recognition. So we want to be able to take the labels that we find on the map and do the recognition so we actually know what the characters and words that are actually on the map. And there's really a series of 3 steps we're going to do for this. The first is to automatically locate the text string. It sounds easy because people are very good at this, but we have to actually find the text strings and the actual orientation of those strings on the map. So we find the strings, we're going to detect the orientation, and then what we do is we actually rotate those strings so then we can run off-the-shelf optical character recognition software on it. We thought rather than reinventing our own OCR software, there's lots of good commercial tools out there. But the problem with the commercial tools is they all assume that you have the text string located horizontally going across the page, and that's not the case with maps. So that's the final step. Okay, so let me give you a sense for the different steps here. So here on the left, we start with the text layer that was extracted. Notice this is just the text layer. We were able to pull this out separated from the road layer. We go through a dilation step, okay, and then we look at all the connected characters here. And you can see this does a pretty good job of just detecting the location of the text strings, except that some of these strings, you can see here, this large box of strings that are all connected together, because on some maps, they end up, strings that go in different directions, they end up putting very close to each other. And so you end up with these big blobs of text. So we have to have some way of actually teasing apart these different text strings here. So we go through another step here where we essentially look at the size of these, the larger blocks here, and we do some additional processing to essentially look at the angle of the characters with respect to each other, right? What's the general direction of the characters? And doing that, we can then pull them apart. So here we have Olympian in Washington and Hadley Way, which are all sort of superimposed on top of each other. And we don't know exactly how to pull them apart, but what we do is we leave that to the OCR software, but rather just sort of say, well, we think there's at least at least three different strings here. One that corresponds to Washington with some, extra pixels. You can see the N and the Y come very close to Washington. And likewise, in Olympian, we end up with this W here. And so we don't try to separate out these pixels. We just generate two different strings and say, okay, we're going to generate one for Washington and one for Olympian with some extra stuff in there. Same thing with the Way here in Hadley Way. We end up with this T from Washington sort of superimposed here. But once we do that, then we end up with this nice green layer down here where you see now we've actually broken up the text strings into all of the separate components, right? So we actually have all the individual text strings identified and their general orientation. But you can see the boxes are still large here, right? So if you look at the box around Olympian, you can see that we don't really know the exact orientation of Olympian yet. So the next step is to actually figure out the orientation, the precise orientation of this text string. So if you take, what we do is we take the string Olympian and we actually generate a set of orientations for it and then run through a technique called run length smoothing, which essentially generates what's called this closing operator, where we're going to fill in some pixels on these strings and then go through an erosion step. And the interesting thing is that once you get the correct orientation, then the result of this erosion step is you're going to be left with the most number of pixels in it. So we can essentially use this to determine the exact orientation of the string. Once we do that, we take the correct orientation, then we can run it through a commercial OCR system, which will then do the recognition. And a string like this, it has no problem recognizing this as Olympian. It'll generate the text string, and because we've done the registration of the map with the imagery or the vector data, we also know the precise lat-long coordinates of the actual string, so we can actually not get just the text string, but also its location. So in terms of results, so here are results. Here are some earlier results. We have more recent stuff I'm not going to present today. But the earlier results show on two different maps. On the left, we have a Rand McNally map labeled RM in the table. And on the right, we have this tourist map, international tourist map, labeled ITM in the table. And you can see the results are actually quite good. Character level precision, which is going to be the measure of how much noise you introduced, is over 95% in both maps. And then the character level recall, shown in the second column here, is 93% for the Rand McNally map, 95% for the international tourist map, which is really quite good for doing automatic recognition, because you can look and see there's a potential for a tremendous amount of noise on these maps. Word level and precision recall is lower, and that's simply because for any one mistake for a character, right, means that you're going to get the word wrong, and so you expect the precision numbers to be a little bit lower for these. So here we ended up with precision in the 76 to 81% for these two maps, and for recall, word level recall, 79% to 85%. But I view these as preliminary results because we have some ideas for techniques that we can employ on top of this, where I think we can get much higher numbers in terms of to get word level and precision recall into the 90% level. Okay, so that brings me to sort of related work in conclusion. There's lots and lots of work, related work on map processing. I mean, people have been doing map processing for the last, 20 or 30 years. Some of the older work on map processing focused on, stuff that was done in the 70s and early 80s, focused on, problems of just how to store the maps, because back then they were so large in terms of size, and how to actually see the maps, and then a lot of manual techniques. More recently, people have developed techniques for various components, so we build on a lot of other people's work and the work we've done. But I think the single largest thing that distinguishes our work from previous work is that most people in the past focused on a single type of map, right? Usually they start with the problem that, okay, I've got the USGS topo maps, and the problem is how do I actually create the layers from this particular type of map? And they tended to focus on one type of map, and they optimized their techniques for that type of map. What we've tried to do is to essentially say, all right, we want to be able to handle any kind of map. Well, we make some assumptions. We assume the map's drawn to scale, that it has a road network on it, and that we know the orientation of the map. But otherwise, we assume we want to be able to handle any map that sort of falls within those requirements, and to minimize the amount of user effort required to actually do that. So a lot of the techniques, I'm not going to go through the individual techniques, have focused on specific types of maps and or specific pieces of the map processing. And there's been, this is just a brief survey of some of the work. There's a lot of work out there on map processing. Okay, so to conclude, what I presented today is, a general approach to essentially discovering, going out and finding maps automatically, registering the maps where we would determine the actual geocoordinates and the details of every intersection point and how it corresponds to some other layer, and then extracting the features from these maps. The new contributions in this work include this ability to automatically identify a map from other things that are not maps, the techniques to extract road layers and text layers from poor quality maps that I described, our approach or algorithms for automatically determining the geocoordinates of the map, and then our work on feature recognition, where we build these accurate intersection templates, and in turn use that to build the road vector data from the maps and to extract the text labels from the maps. There's lots of applications of this kind of work. One obvious thing is simply annotating imagery, right? If you're just looking at an image of an area, you may not really know what you're looking at. But if you can bring maps in automatically and overlay them on top of the image, then you can use that to automatically give you context and understand the actual imagery. We can use it for creating and updating maps. One interesting thing I was surprised by is we would take commercial maps and do this automatic registration and overlay them on the imagery, and you would discover there are a lot of mistakes in commercial maps. You'd be surprised how many mistakes are actually in the maps, and they're very easy to see when you overlay them. But also building maps for areas we don't have good maps for. And the last one is constructing gazetteers. So one of the big challenges is that people are always looking for very detailed sort of features, geocoded features, that they can use for linking other kinds of information and stuff. And so one thing you can use maps for is actually building these gazetteers automatically from all the different map sources that are out there. Last slide here. So if you're interested in learning more about this, almost everything I talked about, everything I talked about today is actually described in, some of our publications. So the first publication here on the top is a recent paper we presented at the Document Recognition conference that describes sort of the overall approach and techniques and stuff. And then we have detailed publications on all the individual pieces that I described today. And these are all on my webpage. If you just Google my name, you'll find my webpage, and you can go and search for all the papers on this topic. Okay, I think we have a few minutes of questions. Thank you. Yes. Okay.
So, for the registration part, how much information do you need to know before you do the registration? Do you need to know it's a map of this city, and then you figure that out, or you?
Excellent question. Okay, so the question was, how much information do we need to know about the map in order to do the registration? Currently, we assume either we know the name of the city or the bounding box that the map falls in. But that's a problem that I want to get back to, because I think there's ways that we could actually completely automate that. One of my goals is to be able to just feed it a map and say, okay, tell me exactly what this is a map of. And so I have some thoughts about how to solve that problem, but we haven't fully solved that yet. But today, it's just the general area of the map. Question over here?
You talk about extracting road features. What other kinds of things have you been working on extracting? Such as area features, lakes, political boundaries, buildings?
Yeah, excellent question. So the question was, what other features have we worked on extracting? There are many different interesting features. You mentioned parks and buildings. We've focused almost exclusively on road and text features. But in general, based on the work we've done and the maps we've seen, I think that the work we've done in extracting the road layers would extend very easily to pretty much any feature layer. And we just haven't worked on it. Partly because we wanted to do roads because we can actually then use the roads for doing the registration, and we wanted to do text because then we could then label the roads. But I think it'd be very interesting to then go on and do political boundaries, parks, all the water features, and so on. They're often shown in different layers and different colors, and so that's why I believe that the techniques for doing road features would extend very nicely to the other features. Yes?
It's like towards the beginning here, your step of erosion and dilation to account for the removed text would be very susceptible to eliminating features like cul-de-sacs, places like that. Have you considered incorporating the information for which pixels you've modified into that stage?
Let's see. We do. Okay, so the question was the following, which is that the erosion and dilation operation, do some distortion of the actual information of the actual road pixels. And so the question is, have we considered actually using the original pixel locations to help us recover information that might correspond to things like cul-de-sacs and stuff? The answer is yes. I mean, one of the things that is happening here is that you're right. When we're doing the processing on the road features, there is some distortion that happens. But a lot of what we're trying to do here is to actually recover enough information from the map to actually first do the registration and location of the intersections on the map. And once we have that, then we essentially can go back to the original road pixels and do the extraction of the road pixels. Right now, we're doing the extraction from essentially the pixels that are after we've actually reconnected the road networks. And that's partly just because it's easier to do it. It's easier to do the mapping on that. But it would be worthwhile to go back and look at some of the more subtle things that happen. Because you're right, when it gets to certain kinds of features like the cul-de-sacs you mentioned, or the other place we see problems are in things like exit ramps and entrance ramps to freeways, because they have sort of unusual angles and stuff that tend to get distorted by those features a lot. So it would be worthwhile to go back and look at the original pixel locations to try to recover that information. We don't do that in the current system, but I think it's something we've talked about, and just haven't integrated it yet. Michael.
You showed a USGS topo map. Have you ever tried extracting contour lines from topo tracks?
We did actually, and it turned out that was actually quite a natural thing to do on the USGS topographic maps, because the topo lines are typically shown in a different color. And so just like we can do the road layer, we can do the same thing with the topo line to pull this out. Yes?
Do you have any challenges registering maps over historical time? So 20 years ago, 10 years ago, 5 years ago, where there are new roads, new street roads?
That's a great question. It's something that I've just started to think about and have been working with some other folks to put together a proposal. Because one of the opportunities here is, now that we can do this processing on sort of a wide variety of maps, is to look at maps over time and look at historical data. And my intuition is that we don't require a very high threshold to actually be able to link a set of a map to the location in terms of the number of matching intersections, because it really has a lot to do with the layout of the intersections. And my intuition is that roads tend to be relatively monotonic in the sense that people put in roads and then they build more roads and they build more roads, and they do move them around from time to time, but not a lot. And so I think that if you look at historical maps, that we probably could do a very good job of being able to link them over time. We haven't done it yet, so it's really just a hypothesis, but I'm hoping to actually get some funding to work on that. Hey, Sebastian.
Did you ever read the Google Terms of Service agreement?
Oh, yes. Yes, I've read them. And I don't think we've violated them either. Road tracing aerial imagery. You mean as opposed to doing it from maps at all?
Yes, so the determined source of information is coming in freeway, you might be able to see roads.
Yes.
And things like label systems and map-based approach.
Yeah. So in fact, right, the other obvious approach to doing the question that Sebastian asked was, have we ever considered looking at aerial imagery and just doing the extraction of the road lines just directly from the aerial imagery? And that's the other obvious competing technique here to get the road locations. And people have been working on, extracting roads from imagery for many, many years. And in general, it's a hard problem. And it's hard for a couple reasons. It's hard because, first, roads are often obscured by other features. So one big problem is that you end up with trees often blocking the roads, so you can't actually see the location of the roads. Sometimes they get around that by, in cold climates, they collect the imagery, in the winter when the leaves are off the trees, but that doesn't always work with evergreens. The other problem is that in, cities with large buildings and stuff, then the buildings often can obscure the roads and stuff. So it can be quite challenging to get the data off the roads, off the aerial imagery. And the other problem is that simply road colors. So we actually did a different project where we looked at automatically aligning road networks with imagery. And so we had to do some extraction of the road pixels from the imagery. And one of the big problems is simply that the road colors are not consistent, not like on a map. So often you'll find people's driveways, the rooftops and stuff can actually have the same pixel colors as the roads themselves. So there's a bunch of challenges in terms of getting the road data directly from the imagery. I think one of the interesting things that we have explored a little bit is combining the two, right? That, if you combine the fact that maps give you the general location for the roads and the imagery gives you the detailed information about the roads. That we did a small pilot project with another group to look at if we could actually combine the two and improve the actual extraction of the road lines from the image by using the information from the map. But I think there's a lot of information that are contained in maps that you can't easily get directly from the imagery.
It seems like in your examples, these were relatively modern maps, except for some of the topos that go back a long ways and are fairly canonical in their layout. But I'm just first part of the question then is to what extent you can apply this to historical maps. It seems like there's probably some like 1920 or 1890 or something beyond which maybe it's harder for your technique to be applied. I'm curious about your reaction to that.
Yeah. So the question was, to what extent our techniques will actually apply to historical maps. So one of the interesting things is, one of the assumptions that we make is that the maps are actually drawn to scale. And, if you look back in terms of mapping, map technology, in terms of being able to draw accurate maps, I think they've developed quite good techniques in the mid to late 1800s. And so, based on what we've seen, we believe that, as long as the maps are actually done to scale or more or less to scale, there's some cartographic license that happens in maps. But if there's a general scale to the map, then we believe that we can actually go back and do many of these historical maps. Just recently we've looked at a number of maps from places like China that go back into the 1900s and late 1800s. And the pixel colors for roads tend to be quite consistent. The fonts, it's interesting, even the fonts, were done by hand, but the way they did them on many of the historical maps before they did computer typesetting was they would build a stencil for the actual characters, and then they would use that stencil to actually draw all the characters on the maps. So the character shapes are actually quite consistent in terms of recognizing the characters. So I would say in general, we can do historical maps that were done to scale and use some standard templates in terms of the actual lettering or characters on the maps.
So then the second part of the question, that your technique seems to have one bookend at around 1850 or so.
Yep.
But the other one would be, so many of the modern maps should be under copyright restraints. And as you get more modern, you have vector data that behind the map that might be available. So I'm just wondering to what extent you feel the technique is really most promising in terms of the available data.
Right, okay, so the question is what extent the techniques are going to be applicable to sort of the available data, given that you have issues of copyright and the fact that some maps could just be generated from the vector data. The vector data may be available to actually create them. That's a really good question, and I think it depends very much on the application. So, I think even today, there's many interesting sort of research problems that we could actually solve by just being able to pull out the maps that you wouldn't necessarily be violating, IP issues. And as I was discussing with Michael, the IP issues vary a lot from one country to the next. And so, you know, in some places you can actually extract things like the text information without necessarily violating the copyrights. In other places that might be an issue. And then, you know, it depends very much on the actual application that you want to use it for. So we're talking to various social scientists and such that are really interested in being able to look at road networks and how they developed over time. And then other people we've been talking to are very interested in, you know, being able to build very detailed gazetteers for other kinds of applications. And, you know, both of these things are things that I think are very compelling uses of the technology that wouldn't violate any of the IP issues. Other questions? Okay. Well, thank you very much.